Good morning, students. In previous class, we have seen what about that valence bond theory and how it has explained the magnetic properties. All those things we have seen. In today's class, we will go through what are the drawbacks of valence bond theory. First, drawbacks of valence bond theory. First one, it is involved with maximum assumptions. It is involved with maximum assumptions. Valence bond theory, it has involved with maximum assumptions only. Assumption is total imagination. Okay, next, second one, quantitative interpretation of magnetic data. Meaning of this quantitative interpretation of magnetic data. See, here itself we will get the doubt, that is why that electrons are involved in pairing with inner orbitals in some complexes. Okay, in some complexes they are not involved in pairing with inner electrons. That clarification was not given. Quantitative means what is the quantity? Why that electrons are not pairing with inner electrons in some complexes? Okay, that clarification. Quantitative interpretation of magnetic data. It gave successfully which is diamagnetic substance and which is paramagnetic substance clearly. But why that electrons are involved in pairing? That clarification was not given. That point will be coming here. This point. This is remained as drawback. Quantitative interpretation of magnetic data. Next. Third one. Quantitative interpretation of thermodynamic and kinetic stability of complexes. Those coordination compounds stabilities were not explained by valence bond theory. Okay, some compounds are very stable, some compounds are less stable. Okay, why those compounds are highly stable and why some compounds are less stable? That quantitative interpretation of thermodynamic and kinetic stability of complexes was not explained by valence bond theory. Third one. Fourth, not explained colors of the complexes. Why these complex compounds? Already I told you, complex compounds are also called coordination compounds. Why these coordination compounds are colored in nature? Actually, maximum every compound will show color. Okay, what is the reason they are showing color? That color nature was not explained by valence bond theory. First one, this is involved with maximum assumptions. Second one, quantitative interpretation of magnetic data was not given by valence bond theory. Third one, quantitative interpretation of thermodynamic and kinetic stability of complexes also was not explained by valence bond theory. Stability of complexes. Okay, not explained color of complexes and couldn't classify weak and strong ligands. Couldn't classify weak and strong ligands. Okay, once see towards the board now, all of you. Totally 5 drawbacks of valence bond theory I wrote on board. What are those? See all of you. First one, this valence bond theory is included with maximum assumptions. Okay, second one, quantitative interpretation of magnetic data was not given. Third one, quantitative interpretation of thermodynamic and kinetic stability of complexes. Fourth one, not explained color of complexes. And fifth one, couldn't classify weak and strong ligands. Okay, some ligands are strong ligands and some ligands are weak ligands. The classification was not given by valence bond theory. So to explain the drawbacks of this valence bond theory, next theory was proposed by name crystal field theory. Okay, that is given as CFT. Okay, ma. Now let us start with the crystal field theory and what are the successful explanations of CFT we will see. Okay, ma. Till now we have completed valence bond theory and drawbacks of valence bond theory. I hope you are all clear about this. Now we will go through next theory, that is crystal field theory. Very important concept, ma. Under this crystal field theory, directly instead of going into the theory, we have to know first initially about degeneracy. Degeneracy and degenerate orbitals. Degeneracy and degenerate orbitals. Okay, first what is meant by degeneracy? The property of orbitals contained by same energy. The property of orbitals contained by same energy. That property is called degeneracy, and those orbitals are called degenerate orbitals. What is that? Say again. The property of orbitals contained by same energy. The property of orbitals contained by same energy is called degeneracy, and those orbitals are called degenerate orbitals. For example, totally d orbitals are 5. dxy, dyz, dzx, dx square, y square, dz square. In atomic structure we have seen already, these 5 d orbitals contain same energy. These 5 d orbitals contain same energy. If they are belonging to 3D or 4D, whatever it is, these 5 d orbitals contain same energy. Then those orbitals are called degenerate orbitals, and the property of orbitals contained by same energy is called degeneracy. Okay. Another example, if you take 3 p orbitals, px, py, pz. These are examples for degenerate orbitals, and the property is called degeneracy. Okay, even if you take f orbitals, total 7 f orbitals are there. All the 7 f orbitals are degenerate orbitals. Okay, are you clear about degenerate orbitals and degeneracy? Okay, now next thing is we have to know the structures of these 5 d orbitals. Already you know, but one more time I am going to draw that one. Let us see. First one, dxy. This is x-axis and this is y-axis. Next, second one, This is y, this is z axis. Next, this is dyz. This is x, this is z. This is dxz. Next, remaining two orbitals are this is x-axis, this is y-axis. This is dx square y square, and next z. This is dz square. Totally 5 d orbitals ma. In your notes also draw these 5 d orbitals, all of you. Okay. Why I am explaining these shapes, and why I am saying that to draw the diagrams in our notes. That one you will understand. First note down in your notes, all of you. Totally 5 d orbitals are there. Out of 5, dxy, dyz, dxz. Fourth one, dx square y square, dz square. Okay, and here observation point is, all of you observe carefully. Above I have drawn 3 orbitals. Those 3 orbitals lobes are in between the axis. 3 d orbitals lobes are in between the axis. See, this is axis, this is axis. In between the axis we have. Next, remaining 2 orbitals are there na? Remaining 2 orbitals lobes are along the axis. That is the observation point here we have to do. 3 d orbitals lobes are in between the axis. This is axis, this is axis. In between the axis we have 2 d orbitals lobes are along the axis. Okay, that's why scientists they classified these 5 d orbitals into 2 sets. Scientists they classified these 2 d orbitals into these 5 d orbitals into 2 sets. Those are one set contains these 3 orbitals, that is called T2G set. One set contains 3 d orbitals which are identical, means in between the axis we have. Lobes are present in between the axis. Okay, those 3 they selected and they kept it under the name T2G. Next, these 2 orbitals are one set which is called EG. This is small t, now this is small e. In your notes itself, like this, note down, no problem. Okay, these total 5 d orbitals are made into 2 sets. Those are T2G set and EG set. You can remember T means triplet, 3 are there na? T. But what is this 2G, this EG ma? That explanation once I will differentiate that one. But before that, total 5 d orbitals we have. Okay, that 5 d orbitals are made into 2 sets. One set contains 3 orbitals which is called T2G set, and next set contains 2 orbitals which is given as name EG set. Okay. T2G set contains 3 orbitals ma, dxy, dyz, dxz. EG set contains 2 d orbitals, those are dx square, y square, dz square. Okay, next point. Finally, I am going to write one more time. P2G set contains dxy, dyz, dxz. Next, EG set contains dx square, y square, comma, dz square. Sir, why did they make into two sets? Now you will get clarification. Now coming to the point. Totally 5 dr terms are there. dxy, dyz, dxz, dx square, y square, dz square. Okay, all the 5 d-orbitals have same energy. That's why they are contained by the property degeneracy. All the 5 d-orbitals have same energy. That's why they have the property that is degeneracy. Till how much extent they have degeneracy? In the absence of any field from outside. In the absence of any field from outside means any magnetic field, okay, any ligands, anything. In the absence of those things, okay, suppose when ligands are approaching, these 5 d orbitals are not contained by same energy. Splitting will be happened. That is only I am going to say. Okay, so in the absence of ligands, one more time. In the absence of ligands, these 5 d orbitals contain same energy. They contain degeneracy. When ligands are approaching towards the central metal atom, one more time. When ligands are approaching towards the central metal atom, these 5 d orbitals will lose degeneracy. That means they are no longer contained by same energy. They will be made into two sets. Identical orbitals are there na? dxy, dyz, dxz. This is T2G set. Okay. dx square, y square, dz square. This is EG set. Observe this one carefully, all of you. These 5 d orbitals are there now. These 5 d orbitals will be contained by degeneracy up to ligands approaching. At once ligands approach the central metal atom ion, one more time. At once these ligands are going to approach the central metal atom or ion. These 5 d orbitals are split into two sets. Okay, dxy, dyz, dxz are identical na? They are made into one set. Higher energy or lower energy. That one according to complex I will say. Okay, for your understanding purpose, simply I have written splitting of orbitals into different energies. This set is contained by one energy. This set is contained by another energy. Difference in energy is there or not? This degeneracy will be lost. Okay, in the absence of any ligands, one more time, these 5 d orbitals contain same energy. In the absence of any ligands, these 5 d orbitals contain same energy and they have the property of degeneracy. At once ligands approach towards the central metal atom or ion, they will lose the degeneracy and their energies are getting different. One set is contained by 3 orbitals and another set is contained by 2 orbitals. The set which contains 3 orbitals is called T2G set and the set which contains 2 orbitals is called EG set. Okay, observe the diagram all of you. This process of splitting 5 d orbitals into two sets is called crystal field splitting. This process of splitting 5 d orbitals into 2 sets is called crystal field splitting. As this theory is entirely depending on crystal field splitting, this theory is called crystal field theory. The process of splitting of these degenerate orbitals into 2 sets is called crystal field splitting. Okay. Crystal field splitting, as the theory is depending on entirely this crystal field splitting, that's why this is called crystal field theory. Okay, ma'am. Now, what about the splitting in octahedral complexes and what about the splitting in tetrahedral complexes? We will see. Okay. Now, next side heading is crystal field splitting in octahedral complex. Okay, crystal field splitting in octahedral complex. Before that, I would like to explain that octahedral structure first. After that, I will come to this splitting one. Okay, before that, all of you, first thing is my question: what about crystal field splitting? The process of splitting of these 5 degenerate orbitals into 2 sets is called crystal field splitting. Okay. Now we are discussing this crystal field splitting in presence of in octahedral complex. Okay, let us see now how this octahedral structure will be presented. We know this is the plane. This is the central metal atom. Okay, here ligand will be there, L, ligand, L, L, in plane. From above the plane, we have one more ligand. From below the plane, we have one more ligand. Correct? From above the plane, we have one more ligand, and below the plane, we have one more ligand. To form this type of structure for metal atom, ligands, they will find a easy way to approach towards the central metal atom. Ligands, they will find one easy way to approach towards the central metal atom. Okay, see, just imagine this is x-axis. This is y-axis. And this is z-axis. If ligands approach along the x-axis, along the y-axis, and along the z-axis, see all of you, these three are axes. Okay, this is x-axis, this is y-axis, and this is z-axis. Now, ligands are approaching towards the central metal atom along the axis, along x-axis, along y-axis, or along z-axis, because to be less repulsion, to maintain the less repulsion automatically, okay, this octahedral complex exactly with 90 degrees. What is the angle between this ligand and this ligand? 90 degrees. Okay, to be maintained with 90 degrees, generally that ligands will approach towards the central metal atom along the axis. Are you understanding now? When ligands are approaching along the axis, see, we have 5 d orbitals, dxy, dyz, dxz, dx square, y square, dz square. When ligands are approaching along the axis, the orbitals which contain lobes along the axis, those orbitals' energy increases because of repulsions. These ligands will apply repulsions on the axes which are present along the orbitals which contain lobes along the axis. One more time I am going to explain now. See all of you. We have 5d orbitals. Okay, out of 5d orbitals, 2d orbitals contain lobes along the axis. Remaining 3d orbitals contain lobes in between the axis. Okay, now what did I explain? To form the octahedral complex, ligands will approach along the axis to form the octahedral complex with the angle 90 degrees, correct? Between one ligand and another ligand, every angle will be 90 degrees. So definitely these ligands will approach along the axis. When ligands are approaching along the axis, they will apply more repulsions on orbitals which contain lobes along the axis. 5d orbitals are there. Ligands are going to form bonds with d orbitals only. Ligands are going to form bonds with 5d orbitals. Okay, out of 5d orbitals, 2 orbital lobes are along the axis. So these ligands will apply repulsions on these 2d orbitals highly. Because of this, these 2 orbitals energy increases, remaining 3d orbitals energy decreases. That splitting is called crystal field splitting in octahedral complex. Now I will show how it is happening. Okay, ma? See all of you. First, we have 5d orbitals. dz square. Initially, because of ligands, before ligands approaching, because of the repulsions, all the orbitals energy will be little bit increased. All the orbitals energy, first it will be little bit increased. Next, now ligands are approaching along the axis. Which 2 orbitals contain along the axis? Dx square y square dz square. These 2 orbitals energy increases. This is dx square y square dz square, and this set is called Eg set. And remaining 3 orbitals are there. Those energy decreases to maintain the overall energy same. Okay, dxy, dyz, dxz, and this set is called T to G set. Okay, and this is the crystal field splitting in octahedral complex, which is represented by delta O. O means octahedral complex, delta means difference in energy. This delta is nothing but difference in energy between Eg and T2G set, and O is called in octahedral complex. Okay, this representation is representing crystal field splitting in octahedral complex. See towards the diagram, all of you. First, all the 5 d orbitals energy will be little bit increased. From there, splitting will be happened. Okay, why that dx square y square dz square we wrote on the above? Because those orbitals contain d lobes along the axis. Then here, ligands in octahedral complex, they are approaching along the axis. So those ligands will apply more repulsions on dx square y square and dz square orbitals. So those 2 orbitals energy increases. because of the repulsions, those 2 orbitals energy increases and remaining 3d orbitals energy decreases. Okay, the splitting which is happened in presence of ligands is called crystal field splitting, which is happened in octahedral complex. That's why we represented that delta means difference in energy of Eg set and T2G set in octahedral complex as delta naught, that is delta O. In the same way, we are going to represent in tetrahedral complex also. Now we will see. Before that, observe this diagram carefully, all of you. Reason also it is very clear. While the formation of octahedral complex, ligands are approaching along the axis. So the orbitals which contain lobes along the axis, those energies are increased. Those are dx square, y square, dz square. So those are above, and remaining 3d orbitals are there na, dxy, dyz, dxz. Okay, those 3 orbitals are below. The difference in energy between Eg and T2G set is called delta O. Now we will see what about in tetrahedral complex. Okay, ma? Crystal field splitting in tetrahedral complex, and this one will be getting reversed because what is the shape of tetrahedral? Like this. While the formation of tetrahedral complex, suppose imagine this is x-axis, this is y-axis, and this is z-axis. Correctly, if you draw, this tetrahedral complex will be formed. Tetrahedral complex will be formed when ligands are approaching in between the axis, not along the axis. Okay, angle 109 degrees 48 minutes. To maintain that 109 degrees 48 minutes, definitely these ligands will approach in between the axis. Then what will be happen when ligands are approaching in between the axis? The orbitals which are present with lobes in between the axis, those energy will be above, and remaining orbitals energy will be below. Means those orbitals energy will be increased. Then this one will be reversed. Below we have 2d orbitals, no? Above we have 3d orbitals. This is T2G set, and this is Eg set. This is dxy, dyz, dzx or xz. This is dx square, y square, dz square. This is in tetrahedral complex. Now, which orbitals contain lobes in between the axis? Which orbitals contain lobes in between the axis? Those orbitals energy will be getting increased because of repulsions between ligands and those orbitals highly. Those orbitals are getting high, and these orbitals are getting low. And this splitting is represented by, this energy difference is represented by delta T. Delta means difference in energy between the two sets. T is nothing but in tetrahedral complex. This is delta T. Draw these two diagrams neatly, all of you. Crystal field splitting in octahedral complex and crystal field splitting in tetrahedral complex. Carefully draw these two diagrams. Okay, and one more term I am going to say. That term is capital P. That one I will introduce. Before that, I hope you are clear about this crystal field splitting in octahedral complex and tetrahedral complex now. Okay, see all of you. The new term is called P, which is called pairing energy. What is that? P, which is called pairing energy. Definition of this pairing energy is, if you take orbital, single orbital I took, first electron is present. While second electron is entering into the orbital, it is getting paired with first electron with opposite spin. Already one electron is there with clockwise spin. Another electron is entering into that orbital with anti-clockwise spin. At that time, some amount of energy is going to be released. That is called pairing energy. Energy released at the time of pairing of electrons is called pairing energy. Energy released at the time of pairing of electrons is called pairing energy. Okay? Now, see carefully. Splitting diagrams over in octahedral complex and tetrahedral complex, and this theory made ligands into two categories. Those are strong field ligands and weak field ligands. CFT classified ligands into two types, depending on their efficiency to repel. Strong field ligands will repel the orbitals highly, weak field ligands will repel the orbitals weakly. Okay, depending on that strength, to how much extent they will repel the orbitals, ligands are classified into two types, strong field ligands and weak field ligands. Example for strong field ligands, Cn minus, weak field ligands F minus, Cl minus, etc. That order is also there, that is called spectrochemical series. In the next class I will say that order. Before that, crystal field theory, this is one of the drawbacks in valence bond theory. Valence bond theory could not classify ligands into strong ligands and weak ligands, but crystal field theory made that ligands into two categories, strong field ligands and weak field ligands. Example for strong field ligand, Cn minus, NH3 is also strong field ligand. Weak field ligands F minus and Cl minus. Okay, this point was also successfully given by CFT. Now, let us observe. Okay, see here, all of you. Suppose 5 d orbitals we have. These 5 d orbitals are split into two sets. One is EG set and another one is T2G set. This is in octahedral complex, and this is splitting energy difference is called delta O. Okay, now for octahedral complex I am saying here, or tetrahedral complex, whatever it is, in presence of strong field ligands the splitting is very high. Why? They will apply more repulsion. One more time. In presence of strong field ligand, the splitting is very high. What is the meaning of that one? They will apply more repulsion on orbitals. Because of that, these EG orbitals will be highly energetic, and T2G orbitals will be very low energetic. The energy difference is same. Okay, how much energy is increased for EG, that much energy is lowered for T2G. So the splitting is very high. Meaning of this one, delta naught is greater than P. In presence of strong field ligands, delta naught is greater than P. In presence of one more thing, delta naught or delta T, anything, the difference is very high in tetrahedral complex or octahedral complex, whatever it is. Okay, so delta naught or delta T greater than P in presence of weak field ligands. In presence of weak field ligands, the splitting is low. So this one will be low only. When it is low, delta naught or delta T less than P. Okay, so what did I write on board? Observe all of you. In presence of strong field ligands, delta naught or delta T means that splitting of energies will be very high, and those delta naught or delta T is greater than P. P means pairing energy. The energy released at the time of pairing of electrons is called pairing energy. Next, in presence of weak field ligand, the delta naught or delta T is less than P. Okay, I think up to this much extent you are very clear. Okay, this is about today's class, na? All of you pay attention till today. What is the thing we completed? Okay, I will recall. First we started with the drawbacks of valence bond theory. After that we have gone through crystal field theory. In crystal field theory, crystal field splitting we have seen that crystal field splitting in presence of octahedral complex, in octahedral complex or in tetrahedral complex also we have seen that two diagrams are very important. After that, crystal field theory made ligands into two types, strong field ligands and weak field ligands. Okay, in presence of these strong field ligands, the splitting is very high, so this delta naught or delta T is greater than P. In presence of weak field ligands, the splitting is low because of the delta naught or delta T is less than P. Okay, till this we completed today. And what are the factors? Means what about the things happened when it is greater than P or this is less than P? That Ohm's rule is violated, like that we have seen that clarity we will get here. In next class, I will take the examples which were explained in valence bond theory, which were failed by valence bond theory, but I will successfully explain by using the CFT. Okay, ma? In next class we will see that examples. This is about today's class. I hope you are clear about this one. Okay, just go through this one, all of you carefully. Any doubts if you have, you can ask me, reach me through WhatsApp. Okay, ma? Thank you all.